Thank you, Angelika, for this introduction. Hello, everyone. I'm Dusan Marcheta from the Department of Astronomy of Faculty of Mathematics. And it is my great pleasure to chair this, unfortunately, last session of this conference, but I'm sure that we will have a lot of gatherings like this in the future. Okay, maybe not in a physical sense like this, maybe more in some traditional way, but I'm sure there will be a lot of events like this in the future. So here we have 13 posters in this session. I will share my screen now in just a moment. Okay, I hope you can see this. And the first poster is the title is Rogue Planets as Mean of Transport. First of all, I want to say that if we planned that every author can give a brief description in 5 minutes, let's say, about the poster. So if somebody of the authors wants to present the work, just be free to unmute your microphones and give us the description of your work. So the first poster in this session is Rogue Planets as Means of Transport by Alexander Nedeljković, professor from Faculty of Philology and Art in Kragujevac. I don't know if is professor here.
No, it is. We do not have any co-author here.
Okay, so if not, we can go on to the next poster, which is by our dear colleague Alexandra Ciprianovic, now in the United States at Fermi National Accelerator Laboratory. Alexandra, are you here?
Yeah, I'm here.
Okay, go on.
Thanks. So first, amazing conference. Bravo for everyone who organized it. So this poster is the work on this poster was in part done while I was still in Serbia at Faculty of Mathematics and also in Mathematical Institute, but part of it, of course, here at Fermilab. And we worked together with people from University of Chicago and Space Telescope Science Institute. And it is related to using machine learning and deep learning to study distant merging galaxies. And you have probably noticed like the exponential growth in machine learning papers in astronomy and basically every other science, but astronomy has always been a good basis for deep learning because you know that we always had huge amounts of data. And so with machine learning allows you basically to be able to model more complex things than with traditional models and actually rely on the tiny intricacies in the data and maybe bypass some of the approximation that you have to do when you do traditional modeling. And it was shown before that deep learning is also very good at distinguishing between merging and non-merging galaxies, but this was usually done only for very nearby galaxies, which are of course much brighter and bigger and well, easier to work with basically. So what we try to show here is that deep learning can also be very successful in finding and classifying and distinguishing between these objects, even if they are very distant. So for example, here we used simulated galaxies from the Illustrated simulation, and these were on Redshift 2. So if you are interested to learn more about the technical parts of the work, you have more details on the poster about the neural network that we used and also about actual results of the classification and searches. And what we've shown here is that actually whether you use very pristine, nice looking images from the simulation, or if you add noise and try to mimic mock catalogs. For example, we try to mimic Hubble Space Telescope observations. Neural network can really very well work even with galaxies that do have noise. But what is also important is that we showed that it is not very straightforward to just use neural networks, in the sense that if you train on one data set, so for example, if you train on nice pristine looking galaxies from the Illustris, that neural network is not going to be able to classify noisy data set that is mimicking real observations. So the continuation of this work that you will soon also probably see being published is going to be about these differences between simulated and real observations, or using neural networks if you want to bridge two, for example, observations from the two telescopes. And this is, of course, going to be very useful for basically any study in astronomy, whether that is translating information from simulations to real or between two types of observations, because normal neural networks that most people use are not very suitable to bridge this like two domains of observations. And so the start of this this whole topic is given on the right of this poster, where we show that neural networks trained on different data, which you can see here on this nice colorful plot on the right, actually look at different regions of the image. So we plot something called GradCam. GradCams are plots where you can see which pixels of the image were the most important for the classification. And if you train on pristine, and if you train on noise images, the neural networks are actually going to look at completely different regions. So it's not straightforward to just combine the data sets. So anyway, more about that also on the poster, but if you're really interested in the topic, we can of course chat afterwards, or you can send me an email. So that's I think enough. Thank you.
We also have a lot of time for discussion. So if somebody wants to ask something, Alexandra, so feel free, just unmute your microphones. We have a lot of time for discussion. Okay, if not, I just want to say that this is really amazing work. This is a emerging field in not only astronomy, but as you said, we are, let's say, we can call us pioneers in this field. So well done, Alexandra, and I hope this work will be published very soon. So we can proceed to the next poster, which is by Alexandra Kolarski and Davorka Gruber from the Technical Faculty Mihailo Pupin, University of Novi Sad, but in Zrenjanin, and Faculty of Mining and Geology from the University of Belgrade. Alexandra and Davorka, are you here? If you want to present your poster, you can do it now.
I think that no one is here, but anyhow, as organizers, I would like to say that we would display these posters like this, even that authors are not here. So all is
yes, I will just leave this for let's say 30 seconds, so that people can see, and also these posters can be seen on the website of the 19th Serbian Astronomical Conference. So if you are interested more in this topic, you can go to the website and see this poster in more details. Now we can proceed to the next poster, which is done by our dear colleagues, Bojan Arbutina from the Department of Astronomy, and Milica Vučetić, also from the Department of Astronomy, and Petar Kostić from the Astronomical Observatory. Unfortunately, the authors informed me that they will not be able to present these posters, so I also invite all interested participants to see this poster at our website. The next poster is by our colleague Ivana Milić-Žitnik from Astronomical Observatory Belgrade. Okay, she's here, so Ivana, please.
Hello, everyone, and thank you, Dusan, for the kind introduction. I will present you a novel, interesting property of asteroid family Ziarkovsky V-shapes. Asteroid families are the results of collisional or cratering events on asteroid, referred to as parent asteroids. The member of asteroid families are clustered in their proper orbital elements close to the proper orbital elements of the parent asteroid. Asteroid family members disperse with time. It was initially considered that asteroid fragments remained motionless in the proper orbital element space. Then, ejection velocities was introduced in evolution of asteroid families, and later it was known that the Yarkovsky effect was mostly a cause of large scattering of asteroids in asteroid families. The Yarkovsky force is the most important non-gravitational effect. That is anisotropic emission of thermal radiation due to thermal inertia. The Yarkovsky effect changes especially semi-major axis of small bodies revolving around some source of heat. Nowadays, we know that after an asteroid family forms, the asteroid's orbit change in the space of proper elements because of gravitational and non-gravitational perturbations. A cluster of asteroids is identified as a family if its boundary in the semi-major axis versus inverse of diameter or semi-major axis inverse of absolute magnitude planes has a V shape, which is dependent on the value of the Yarkovsky thermal effect, spreading on very large time scales. Recently, Bolin et al. 2018 proposed a connection between the thermal inertia and asteroid diameter and revealed that asteroids' Yarkovsky drift rates might have a more complex size dependence than it was initially thought. Our study also proposed that in some special cases, asteroids are drifting faster with larger diameters than previously considered, decreasing on average the known ages of asteroid families. This occurrence could be connected with the limiting value of the Yarkovsky drift speed we have recently calculated, below which asteroids accelerate motion across mean motion resonances, especially across stronger ones. So we decided to investigate the relation between the asteroid family Yarkovsky V shape and the limiting Yarkovsky drift speed. We have used the known scaling formula to calculate the Yarkovsky drift speed in order to determine the inner and outer limiting diameters for the inner and outer V-shaped borders from the limiting Yarkovsky drift speed. The method was applied to 11 asteroid families of different taxonomic classes, origin type, and age located throughout the main belt. Here on figures 1, 2, and 3, we present the results of our calculation on relationship between asteroid family crossed by strong and weak mean motion resonances, families Edeona and Eos, and only by weak mean motion resonances, family Aeolia, and the limiting diameters. We specially observed families crossed by strong or relatively strong mean motion resonances close to the parent body because of interaction between these mean motion resonances and Yarkovsky drift speeds. Our conclusions are follows. In asteroid families, especially in very old ones, which are crossed by strong or relatively strong mean motion resonances on both sides very close to the parent body, at the limiting diameters exists a change in slope of V-shaped border in the semi-major axis inverse of diameter plane. This change of the V-shape could be attributed to the existing necessary strength of interaction between asteroid orbital motion due to the Yarkovsky effect and relatively strong mean motion resonances. The second one conclusion is, in asteroid families, which are crossed only by weak mean motion resonances on both sides very close to the parent body, the limiting Yarkovsky drift speed doesn't have a role in changing the slope of the V-shaped border. The third one conclusion is, resonant asteroids with diameters larger than the limiting diameter are drifting faster over relatively strong mean motion resonances. And finally, the last and the main conclusion is, the location of inverse of the limiting diameter is exactly at the place of changing the V-shaped slope of border in an old asteroid family, which are crossed in the same side by relatively strong mean motion resonance, very close to the parent body in the semi-major axis inverse of diameter plane. That is all. Thank you for very much for your attention. Thank you. Dusan, do you hear me?
Yes, thank you very much, Ivana.
Okay.
I can now open the floor for the discussion. If somebody has a question, just please unmute your microphone.
I think that people can't see my references at the bottom of this poster.
Well, sorry for that. I put it on the full screen mode.
Full screen, so, okay. Okay, I maybe forgot to put the references. Okay.
Probably yes. But if somebody wants, I want to repeat again, wants to see this poster in more details, just please go to the website and download it. One of the advantages of the traditional conferences is that we can see a poster is much larger format than here. So okay. Now we'll proceed to the next poster by Lyuba Slavcheva-Michova and Boyko Michov from our colleagues from the Institute of Astronomy of Bulgarian Academy of Sciences. So here is the poster. The title is Spectral Energy Distribution of MRK 509. Somebody of the authors is present here. I think no. Okay, if so, we will proceed to the next poster by Natalia Jans from the Baltimore, United States, and collaborators. And the title is Correspondence between Milutin Milankovic and Els Wegner-Koppen. I think that Natalia also.
Yes, Dušan, I'm here. Luka is here.
Luka is here. Okay, Luka, please.
So Natalie cannot be connected with the internet and asked me to say several words about the poster.
Okay.
So poster is one of the, how to say, results that we got during the investigation of collaboration between Milutin Milankovic and Vojislav Mišković. So we have several letters that they are very interesting, and we have new data about the collaboration and the role of the astronomical observatory in the calculations of the theory of Milutin Milankovic. So Natalie also went to the archive of Serbian Academy of Science and Art and found very interesting letters or correspondence between Milutin Milankovic and Elza Wegner-Koppen. Elza Wegner-Koppen is was wife of Alfred Wegener and daughter of Vladimir Koppen. Both of them collaborated with Milutin Milankovic on the theory of Milutin Milankovic. So it is very interesting. We found 3 letters and 1 postcard that is presented on the poster, and it is interesting from a historical point of view to see this correspondence, and we would like to present it to the conference, Serbian Astronomical Conference. So it is. Thank you.
Okay, thank you, Luka. If somebody wants to ask something, please just unmute your microphones. If not, you can also use the chat channel to write the questions if you like. So the next poster is by Veselka Trajkovska, Fragments from the History of the Construction of the Belgrade Astronomical Observatory in Veliki Vračar. Is Veselka here? Let me see. I think no. So this is, I suppose, a very interesting historical retrospective of the construction of the Belgrade Astronomical Observatory. So please download the poster from our website and see it in more details. Now we will go to the next poster by Vladimir Srečković, Ignjatović, and Milan Dimitrijević from the Institute of Physics, Belgrade, and Astronomical Observatory. Vladimir, are you here? Okay, I think Vladimir is not here. Okay, because we have 2 more posters by the same authors. Maybe some of the co-authors. Okay, no. If not, we will go on to the next poster, which is research of the impact of strong solar flares on the lower ionosphere by VLF radio waves and satellite observations, also by our colleagues from the Institute of Physics, Srečković and Šulić. Maybe somebody, okay. Same for this poster, and I suppose also for the next one, which is destruction of some molecular ions of astrophysical interest, also by the same authors as the one of the previous posters. I suppose that this poster will also not be presented here, but I will repeat once again. You can see it on our website. Okay, the next poster is by Zlatko Majlinger, Milan Dimitrijević, and Vladimir Srečković from Astronomical Observatory in Belgrade and the Institute of Physics. Is Zlatko here or Milan? Oh, let me see. Okay, I think no. Okay, we move on. The next poster is an international astronomical research collaboration project in Serbia by Zoran Tomic. I think that Zoran is here. Okay.
Yes,
Zoran.
I'm here.
Okay.
So this is one of the citizen science project that we are doing in Eureka, and this project is more than 10 years old. So the whole idea is to provide a high quality astronomical data to citizen scientists around the world, and especially to students that would like to engage more in astronomy research. So the children and participants are able to make original astronomical discoveries and participates in hands-on astronomy, and it's free for use. So I would like to suggest to all of you maybe to participate in this kind of project, and this is one of the ways how we can promote astronomy more in Serbia. So we started in 2010 to participate. From last year, we organized with them All Serbia Asteroid Search Campaign. So we invite teams from Kruševac and also other parts of Serbia. We had also participants from Bosnia and Herzegovina, especially from Sarajevo. I'm proud that since this year, Astronomical Society Orion from Sarajevo, they are organizing their own event. So they are covering the whole Bosnia and Herzegovina with this project. So usually we have participants from high schools, but also from primary school students and a lot of amateur astronomers. And so we get images from Pan-STARRS observatories. We use Astrometrica software for analysis, and we get the code. So this software is free for use for all the participants. And what is a good thing about this project is that when you finish your research and doing things in Astrometrica, you are learning how to write scientific reports. So, and all by using website and interactive things that they've developed. And when the campaign is finished, and it usually lasts for 20 days, you get on your email certificates for participating, and NASA is also supporting this project. So on this poster, you can see a group of students from, not from Kruševac, but from other cities in Serbia, how they are doing their research in school object. You can see Astrometrica software, how it is used. And also you can see a list from one of latest these projects that we had, I mean, campaigns, and these are all preliminary discoveries that these teams from Serbia have made. So I invite you to research more about this project on isaac.cosmicsearch.org, and maybe to use this software and project as a good tool to promote astronomy. Thank you.
Thank you, Zoran. I would like to say that I'm a huge fan of citizen science projects. I think this is, unlike classical promotion channels, this is, in my opinion, the most effective way to promote the astronomy, because unlike other promotional channels in citizen science project, ordinary people have impression that they are involved in some professional scientific context, and that they give some real contribution to the science. And I can see that in some real professional research projects, scientific project, citizen science projects become very important parts in the dissemination part. So this is excellent, and I think we should have more projects like this. Okay, if somebody else has a comment. No. Okay, if not, I'll proceed to the last poster of this session by Jasmina Horvat and Ana Budragovic. Jasmina is here. Before you start, I want to emphasize that Jasmina Horvat is a bachelor student at our Department of Astronomy, and she was working hard during the summer. And here now you can see the results of this hard work. Jasmina, please.
Hi, can you hear me?
Yes.
Okay. Hi, everyone. My name is Jasmina Horvat, and I will present my work done during the summer practice at Astronomical Observatory in Belgrade. I've been working with Ana Budragovic, and I've chosen to learn surface brightness modeling. We decided to use SDSS Stripe 82 because they are very deep, and the SDSS Stripe 82 survey is 2.5 degree wide region along the celestial equator. And this region has been imaged repeatedly 80 times in all SDSS filters. These images were co-edited, taking special care of background subtraction, and in the final co-edited images, surface brightness limit raised was 28.5 magnitudes per arc second square in airband. NGC 941 Galaxy was analyzed in detail in the paper of Backus et al. From 2012. And in the paper, authors investigate the relation between classification of spiral galaxies light profile as type 1, 2, and 3 with stellar halos. To remind you, light profile of minority of spiral galaxies shows a simple exponential decline, while the majority, approximately 90% of them, show either up or down bending profiles. We have modeled the light profile of galaxy NGC 941 using GALFIT code that create models in 3 dimensions. And when multiple components are fitted, each of them represents a true physical component. And the results are shown in the upper left part of the poster: galaxy image, galaxy model, and residual image, respectively. And in the residual image, the remnant of spiral arms is visible. This is because we used Sersic function to model spiral arms, so we couldn't remove the pattern, but the flux was modeled successfully. Also, we modeled the light profile in 2 dimensions, applying isophotal analysis that result in a set of concentric ellipses inside which flux intensity is averaged. And in the first image in the upper right, you can see these ellipses. To model properly other parts of the light distribution, we kept the ellipticity and position angle fixed, and then we created a model and subtracted it from input image to get the residual. And you can see this in the next two images. In the residual image, the spiral arm structure is left because it cannot be modeled successfully this way, because isophotal analysis is suitable for elliptical galaxies where there are no additional asymmetric structure like spiral arms, but this fit, although it looks like the one obtained with the Galfit code, is different. It doesn't take into account the point spread function that affect both innermost and outermost region. In the last row, first we show the results from the paper of Backus et al. From 2012, and they claim to have a broken profile downbanding that can be classified as type 2. They have also found a bar in the center shown as a green points, and the halo in the outer part shallow is a yellow point. In the next plot, we show our results from isophotal analysis, blue points, and overplot their points as red points. The most successful fit in 3D is two-component Sersic fit, red line in the composite fit, where one component is exponential profile, disk of the galaxy. It's a green dotted line, and the spiral arm structure as a yellow dashed line. So it seems that it's not a broken disk at all, but the presence of spiral arms resembles the break in the 2D analysis. In the next image, we have tried to fit a broken disk, but in 3D using Galfit, and it can be done. It doesn't look bad in the other parts, but it completely misses the spiral arm structure contribution to the profile, while single disk with spiral arms does the job. If this is true, we don't know. It might be case for a single galaxy, so it needs to be redone for more galaxies. And another thing we start exploring is the stellar halo, and the problem is that the effect of extended wings of the point spread function is important in outer region, and it can artificially make stellar halos larger and redder than it is. We tested this by making the same isophotal analysis with and without the point spread function, and the G minus R color is affected by PSP wings, and to infer how much we would need to do the convolution, which will leave for some future work. Thank you for your attention.
Thank you, Yasmina, very much. I have to say that we are very, very satisfied and proud that our students are so motivated and enthusiastic and willing to invest significant effort to get the results like this during their basic studies. So well done, Yasmina.
Thank you.
If somebody else has a comment, please unmute your microphones.
I would like to comment, if it is possible, Dusan. Thank you.
Yes, yes.
I would like to say that I know Yasmina Horvat as a student during her first year at Department of Astronomy, and she is really excellent student. And this work just is another step in what I believe would be her really bright and successful scientific career. And I would like just to congratulate to Yasmina for this nice work and to thank her being here and presenting this at the conference.
Thank you all, and thanks for the opportunity.
Okay, thank you, Angelka. I can confirm your words, and I would like to encourage students to be involved more in the future events like this. Unfortunately, this was the last poster of this session, and with this we practically finish with the scientific program of this conference. So now I will invite Angelka and Jelena too. To take the word, yes. Yes.
Okay. Dusan, would you like to stop sharing?